I'll do a chandelle.
Okay. Uh-oh. But I'm really having trouble putting this all together today.
Yeah, you seem to be having enough trouble today. It might be a good idea just to go on back.
Okay, well maybe we could go over some of these maneuvers when we get back to the airport.
Sure, good idea.
Okay.
Flying is really exciting, except when you realize that you're not completely confident about some basic flying maneuvers. You thought you knew them perfectly, but now you find out you have some rough spots to work out. Better now than later in your flying career. This program will show you exactly what's expected of you according to the FAA and your instructor in this course. As far as we're concerned, there's only one right set of procedures to do these maneuvers. This program covers fundamentals of flight, basic flight maneuvers including slow flight and stalls and steep turns. You'll also learn about ground track maneuvers including turns about a point and S turns, and we'll cover some advanced maneuvers such as chandelles and lazy eights. All of these will be covered just the way the FAA wants you to know them. Now, let's join Jeff Doder and his student as they refresh their knowledge on flight maneuvers.
Okay, Barb, where would you like to begin?
Well, I think I told you before that it's been a long time since I've been flying, and I'm feeling real rusty with all of this. Maybe we could just do a general review.
Okay, I think probably we need to start at the very beginning and lay a good foundation and then build our way up from there. So we'll start with the 4 fundamentals of flight and make sure we have that down completely and see how that will affect the flight maneuvers, and then we'll move on from there. The 4 fundamentals are straight and level, climbs, glides or descents, and turns. In straight and level, as the name implies, you're trying to maintain a constant heading and constant altitude. I say trying to maintain because you're constantly correcting to keep the airplane where you want it. If the heading drifts off, make a smooth and firm correction to get it back on heading, and then use the flight controls as necessary to keep the heading from drifting again. If the altitude wanders, the same procedure of smoothly correcting back would apply. During flight, we use a combination of outside references and instruments to key us to where the aircraft is and where it's going. We have a picture in our mind of how the airplane should look against the horizon while in straight and level flight, out the nose and out the side windows. When the actual picture varies from what we're looking for, we cross-check with instruments and then correct back with both visual references and instruments. The instruments to be used are attitude indicator, turn coordinator, heading indicator, altimeter, and vertical velocity indicator. Don't fixate on one or the other. Use both or all to keep the aircraft where you want it. And remember that the biggest help in any stage of flying is always to keep the plane trimmed up, so the control forces necessary are very light. Climbs are the second fundamental. During climbs, because of the high power settings required at relatively slow airspeeds, 3 left-turning tendencies come into play. One is torque, second is slipstream, and the third is P-factor. Torque is caused by the spinning propeller. In most aircraft, the propeller rotates clockwise as viewed from the rear. This rotation causes the aircraft to rotate counterclockwise or left wing down, causing the turn to the left. Along with this, the corkscrew or spiraling rotation of the slipstream behind the propeller moves around the aircraft to strike the left side of the vertical tail surface. This causes the tail to move right and the nose to move or yaw left. P-factor is caused by the differential angle of attack of the propeller in a nose-high attitude. The upward moving blade is taking a much smaller bite out of the air than the downward moving blade. This loads the spinning disc of the propeller on the downward moving or right side, causing the nose to be pulled to the left. Both torque and P-factor can be neutralized by the use of right rudder.
So that's why we use right rudder even though we're in a left climbing turn.
Right. Even though we think we're cross-controlling, we're in a left turn, you still need right rudder because of that torque and P-factor.
Okay.
Many of the same visual and instrument references can be used for climbs as with straight and level. The nose of the aircraft will be slightly higher than when level. The wingtips will be similarly arranged against the horizon that will now show a climb attitude. The instruments to be cross-checked are the attitude indicator, vertical velocity indicator, heading indicator, turn coordinator, airspeed indicator, and altimeter. Remember, your forward view is blocked, so during prolonged climbs, make slight turns to clear for traffic in front of you and above you. Glides or descents are the third of the four fundamentals of flight. First, apply carb heat as needed. Pull the throttle back to the manufacturer's recommendation for approach and apply back pressure to keep the aircraft level. As the airspeed bleeds down to approach speed, trim as necessary. Upon reaching approach speed, allow the nose to fall below the horizon to maintain this speed. You should be able to do this accurately with various flap settings as well as clean. Turns are the fourth fundamental. To understand why an aircraft turns, we need to look at the direction of lift. In straight and level flight, the lift vector is straight up, pointing directly away from the ground. As we bank, the lift vector points more to the side, and it's this horizontal component of lift that pulls the airplane around into a turn. As we increase the bank angle, the vertical component of lift decreases, requiring more back pressure to produce a greater lift vector to keep our altitude constant. Probably the hardest part in the performance of accurate turns is to keep the aircraft coordinated while the airspeed and bank angle change. As airspeed decreases, more right rudder is required to keep the ball centered due to torque and P-factor. This will be demonstrated as we perform our flight maneuvers. Remember, all flight maneuvers are made up of these basics: straight and level, climbs, glides, and turns. How we master the rest of the flight maneuvers really depends on how we've mastered these four basics. One of the first basic flight maneuvers that we have to master is slow flight. We practice this to become familiar with and to master the control forces necessary when the aircraft is flying at its minimum speed. Probably the first thing we discover when performing slow flight is the large amount of right rudder required because of torque and P-factor, as well as the relatively large control forces necessary at the slower speeds. To perform slow flight, we must start at and maintain a safe minimum altitude as defined by the FAA. What this usually means is to keep our altitude above at least 1,500 feet above ground level at all times. Apply carb heat if required. Pull back on the throttle to begin slowing. Maintain altitude and heading by adding back pressure and applying rudder as required. Trim to maintain neutral control forces. As the speed decreases to our target speed, add power as necessary. Notice the high pitch attitude required to keep the aircraft from descending. Now the thing to remember is power controls altitude and pitch controls airspeed. If our altitude falls a little, add a little throttle. If our airspeed picks up a little, raise the nose slightly. Practice this straight ahead and with slight turns to either side. Even if wanting to maintain a constant heading, clearing turns should be made to clear the airspace in front of you. The aircraft will turn left easier because of torque and P-factor. Slow flight should be practiced in a clean configuration with partial and with full flaps. Next, let's talk about stalls. Stalls are important to master both during training and afterwards. The important thing to remember is that aircraft does not stall because of airspeed. You can stall at any airspeed, at any attitude, and at any power setting. I'll repeat that. You can stall at any airspeed, at any attitude, and at any power setting. For all stalls, the recovery is the same. Reduce pitch, add full power, and then level the wings. The accelerated stall is a good way to demonstrate that an aircraft stalls because its critical angle of attack has been exceeded. Before performing any stall, clear the area of traffic and maintain a minimum safe altitude of 1,500 feet AGL throughout the maneuver. The highest speed at which you can safely stall is VA, or maneuvering speed. Add carb heat if required. Using a low power setting, roll about 45 degrees and abruptly increase pitch. Since airspeed is relatively high, recovery will probably only need a relaxation of the back pressure. The takeoff and departure stall simulates inadvertently entering the stall during the takeoff phase of flight. First, clear the area. Start the stall a minimum of 1,500 feet AGL plus a buffer. Carb heat as required. Reduce power to slow the aircraft to liftoff speed. As the speed decreases, pull back on the control column to maintain altitude. When reaching the desired airspeed, at full power, use the controls as necessary to maintain coordinated flight and smoothly increase the pitch to initiate the stall. To recover, reduce the pitch, power is already at a high setting, and level the wings if required. These stalls should be practiced straight ahead and in moderate bank turns to either side. For the approach to landing stall, you'll want to start at an altitude higher than 1,500 feet AGL because you will lose altitude leading up to the stall. First, clear the area. Carb heat as required. Set approach power as recommended by the manufacturer. Maintain your altitude by applying back pressure. Lower flaps to a landing configuration. Upon slowing to approach speed, lower the nose to descend at that speed. To initiate the stall, pull the throttle to idle and raise the nose slightly. The recovery is decrease pitch, add full power, and level the wings if required. In addition, raise the flaps to the go-around position if one is recommended by the manufacturer.
I can see that altitude loss is critical, so we need to at least level off, if not establish a climb.
Exactly. These are simulated at a high, or we actually perform them at a high altitude, but these would be happening at a lower altitude, therefore altitude is very critical. So in the practice, whether you're trying to get your license or later on, always think of that as the ground being very close to you, and don't lose any altitude if you can help. Next, let's cover takeoffs and landings. There are three non-standard takeoffs and landings that we need to cover: soft field, short field, and crosswind. For a soft field takeoff, check the owner's manual for recommended speeds and flap settings. Complete the pre-flight checklist and set the flaps before reaching the soft field area. Taxiing should be kept rolling into the takeoff as simulated on this hard surface. Keep weight off the nose gear by keeping the yoke back. As elevator becomes effective, carefully relax back pressure to avoid a dangerous nose-up attitude while keeping the nose gear off the ground. Level off as soon as the aircraft breaks ground to accelerate to best rate or best angle of climb speed. For landing on a known or suspected soft field, survey the field for soft spots, high grass, or obstructions. The approach is normal. During round out, the addition of a little power may help control the touchdown and touchdown point. Land as slowly and lightly as possible, close to a stall, but keep enough speed for full control. After touchdown, power may be added to keep the nose gear from digging into the surface. Keep the weight off of the nose wheel and the aircraft rolling until reaching firm ground. For short field takeoffs, check the owner's manual for recommended flap settings and speeds. Apply full throttle as soon as possible to quickly accelerate. As the best angle of climb speed approaches, begin rotation. Continue at best angle of climb speed until all obstacles are passed. Then ease the nose down to accelerate to best rate of climb speed. For short field landings, check the owner's manual for recommended power and flap settings, remembering that these settings are valid for hard surfaces only. Slow on base, turning final with flaps partly extended and the pre-landing checklist completed. On final, slow to approach speed and extend full flaps. You'll want a steeper than normal approach path. Adjust power and pitch in a coordinated manner to maintain the appropriate flight path to clear any obstacle. If gusty wind conditions are present, add half of the gust factor to the approach speed. Airspeed control is critical. Touchdown near the approach end of the runway. When landing is assured, ease the throttle back, round out, and touchdown at full stall. Keep the weight off of the nose gear, using brakes to stop as soon as possible. For a crosswind takeoff, you want to keep the aircraft on the center line of the runway, using flight controls as necessary to keep the aircraft aligned on the center line during takeoff roll and initial climb out. Use full aileron into the wind at the beginning of the takeoff roll, reducing the aileron as control effectiveness increases. A common error during takeoff is to hold insufficient aileron just prior to and during liftoff. This causes the upwind wing to rise at liftoff. After liftoff, a gentle coordinated turn establishes the crab angle for climb out. To land with a crosswind, first establish the direction of the wind by radio, windsock, or smoke in the area, and plan your approach accordingly. Crosswind landings are quite normal within specified limits, even though flight attitudes may appear abnormal. There are 3 methods to compensate for crosswind. The first is crab into the wind to maintain the flight path aligned with the center line of the runway. The second is to establish a slip by lowering the wing into the wind to kill drift and then using opposite rudder to keep the desired flight path. And the third is really a combination of the two, crabbing and slipping to maintain a center line approach. The airspeed should be normal except with gusty winds, then add half of the gust factor to the approach speed. Before reaching round out, change from a crab to a slip to compensate for drift. The correct attitude during round out is upwind wing low, using rudder as necessary to make a normal landing.
So then after landing, I need to increase the aileron as I would while I was taxiing.
Exactly. As the controls become less effective, you'll need more aileron into the wind to keep that upwind wing from being pulled up by a gust. Next, let's look at steep power turns. The objective of steep power turns is to develop smoothness, coordination, orientation, division of attention, and control techniques while executing high-performance turns. First, clear the area. At the manufacturer's recommended entry speed or maneuvering speed, and on a specified heading, roll quickly into a bank angle of 50 to 60 degrees. Back pressure must increase as bank exceeds 30 degrees to maintain the altitude. Add power as necessary to maintain airspeed. Use outside visual references rather than the attitude indicator, since this instrument will precess during the steep turn. To maintain the altitude, vary the bank and pitch slightly. After either 360 or 720 degrees, smoothly roll out on the original heading and immediately into a turn in the opposite direction. As you roll out of the turn, forward pressure must be applied on the yoke to keep from climbing, and rudder must be used to maintain coordination.
My understanding is that I can change the power to help me roll in and roll out of the turn. Is that
That's
right?
correct. The FAA places no limitations on power control in the flight training handbook. In fact, they say add power as necessary. So if you see airspeed bleeding off, you add a little power. If airspeed is picking up, especially when you roll out, then you want to pull back on the power. Now, when we cover ground reference maneuvers, it means referencing our flight path to the ground, which means accounting for the wind to maintain a specified path over the ground. The first ground reference maneuver we'll review is a rectangular course. During this maneuver, the track of the aircraft is equidistant from all sides of a selected rectangular area on the ground, while keeping the altitude and airspeed constant. This maneuver is basically practice for the traffic pattern. Enter from any direction relative to the wind from 600 to 1,000 feet AGL. In our example, we'll enter with the wind. Since bank angle depends on ground speed in all these maneuvers, our first turn will be a relatively steep bank, and the turn will be greater than 90 degrees since we want to roll out with the required crab angle to maintain the correct ground track. The second turn will be less than 90 degrees due to our crab, and the bank angle will be shallower since our ground speed will decrease as we turn into the wind. No crab is needed as we head upwind. The turn here will be less than 90 degrees and our bank angle will be relatively shallow. The last turn will be greater than 90 degrees and the bank angle will steepen as our ground speed increases. Remember, throughout this maneuver, the altitude and airspeed should remain constant. Next we'll move to S-turns across the road. S-turns across the road is a ground track maneuver where the airplane's ground track describes half circles of equal radius on each side of a straight line on the ground, such as a road or fence line. The road should be approached with the wind at an altitude no lower than 500 feet above the highest obstruction at a constant airspeed. The first turn is started immediately at a relatively steep bank, since ground speed is the greatest. The crab angle is greatest as the airplane flies perpendicular to the wind. As you move along the first turn, gradually lessen the bank angle as the ground speed decreases to maintain the desired ground track. The crab angle is removed completely and the wings become level as the 180-degree turn is completed at the moment the road is reached. Immediately begin a turn in the opposite direction at a relatively shallow bank since ground speed is the smallest. Maximum crab angle is established at the second 90-degree point, and bank angle is gradually increased as ground speed increases. The key to this maneuver is visualizing the desired ground track and then controlling the airplane as necessary to fly that track. Next, we'll cover turns around a point. During turns around a point, the airplane is flown in 2 or more complete circles of equal distance from a prominent ground reference point using a maximum bank angle of 45 degrees at a constant altitude. As in other ground reference maneuvers, a constant radius about a point will, if any wind exists, require a constantly changing angle of bank and angles of crab. The ground reference point should be prominent and away from any buildings, people, and livestock. Enter with the wind so the initial bank will be steepest as you fly abeam the point. As you fly around the point, the bank angle is gradually shallowed out as the ground speed decreases. Also, the airplane's nose is gradually crabbed toward the inside of the circle, so at 90 degrees of turn, crab angle is the greatest. Gradually decrease the crab angle and continue to shallow the bank so that at 180 degrees of turn, the bank angle will be the shallowest. During the upwind half of the circle, bank angle is gradually steepened and the airplane's nose is crabbed into the wind. Now we're going to move to a whole series of maneuvers having to do with eights. Eights along a road, eights across a road. All these are the pattern shown on the ground, more or less describing the figure 8. Although eights along a road may be performed with the wind blowing parallel to the road or directly across the road, I'll only cover across the road since the principles involved are really similar. First, check the area for obstruction clearance and other aircraft. Enter directly above the road, no less than 500 feet AGL. Since the wind is from the side, a crab angle needs to be maintained to keep the ground track over the road. The first turn should be made downwind using a medium bank. As the ground speed increases, the bank angle should be gradually increased so that the greatest bank would be while heading directly downwind. Continuing the turn, the bank should be slowly shallowed out and a crab angle should be added into the turn. Continue to shallow out the bank so that it will be smallest heading directly upwind. The completion of the first turn should be timed so that the airplane will be straight and level over the starting point with enough drift correction to hold it over the road. After momentarily flying straight and level along the road, the airplane is turned into the wind using a medium bank turn. Shallow out the bank as the airplane is turning more directly into the wind, with the shallowest bank again while directly upwind. Continue the turn, adding more crab angle away from the turn, and gradually increase the bank angle. After 180 degrees, continue to increase the bank angle as the ground speed increases with the wind, and decrease the crab angle. In the last 90 degrees of the turn, the rate of turn should be reduced to bring the airplane over the starting point on the road. The rollout must be timed so the airplane will be straight and level, crabbing into the wind and flying parallel to and over the road. An 8 across the road is a variation of 8s along a road and involves the same principles and techniques. The primary difference is that at the completion of each loop of the figure 8, the airplane should cross an intersection of roads or a specific point on a straight road. The loops should be across the road and the wind should be perpendicular to the road. Each time the road is crossed, the crossing angle should be the same and the wings of the airplane should be level. The 8s also may be performed by rolling from one bank immediately to the other directly over the road. An 8 around pylons is similar to the previous two maneuvers, but the ground reference line is replaced by 2 points or pylons on the ground. The pylon selected should be on a line 90 degrees to the direction of the wind and should be in an area away from buildings, livestock, or groups of people. The area selected should be free of obstructions and other air traffic. Throughout the maneuver, a constant altitude of no lower than 500 feet AGL should be maintained. Enter on a downwind heading passing between the pylons. The steepest bank will be necessary just after each turn entry and just before the rollout from each turn, where the airplane is headed downwind and the ground speed is greatest. The shallowest bank will be where the airplane is headed directly upwind. The rate of the bank change will depend on the wind velocity, the same as it does in S-turns and turns around a point, and the bank will be changing continuously during the turns. If the airplane is to proceed diagonally from one turn to the other, the rollout from each turn must be completed on the proper heading with crab angle into the wind. Keep the radius of both turns equal.
So I'm not just making 2 circles, I need to fly a straight section in between each turn.
Exactly. So you're not making complete 360-degree turn. You need to roll out with enough crab angle so that you can intersect the pylon at just the right spot to make both turns of equal radius. A steep spiral is the last ground reference maneuver that we'll cover. Steep spiral is a constantly gliding turn, maintaining a constant radius around a point on the ground, similar to turns around a point. The radius should be planned so that the steepest bank will be 50 to 55 degrees. Start this maneuver from a sufficiently high altitude so that at least 3 360-degree turns may be performed, completing the maneuver above a minimum safe altitude. Add carb heat if required, close the throttle, and establish glide speed. Start a turn of constant radius about a selected point on the ground, varying bank angle due to variations in ground speed as in turns around a point. Clear the engine periodically to prevent spark plug fouling by briefly advancing the throttle to normal cruise power, preferably while heading upwind to keep ground speed changes to a minimum. Maintain a constant airspeed by varying pitch while power and bank angle change.
So after I make my 3 turns, I need to roll out so that I'm set up to make an emergency landing.
Right. Next we'll move to pylon 8s. And pylon 8s, or 8s on pylons, are not truly a ground track maneuver since we make no attempt to maintain a constant radius around a point. Instead, the object is to maintain a line parallel to the airplane's lateral axis and extending from the pilot's eye appear to pivot on the pylon. Now the lateral axis, remember, is the axis going from wingtip to wingtip. So what you're really doing is just keeping the wingtip on the pylon. The 2 pylons should be chosen in the same manner as for 8s around pylons, checking the area for other traffic, obstructions, and proximity of buildings, livestock, and people. Enter the maneuver between the pylons heading downwind. As the first pylon approaches the lateral axis, lower the upwind wing to place the lateral axis directly on the pylon. To keep the wingtip on the pylon, the altitude must be changed slightly as the ground speed changes. If the pylon appears to move ahead of the wingtip, raise the nose slightly to bring the airplane up to the correct pivotal altitude. This will bring the pylon back to the wingtip. Conversely, if the pylon moves behind the wingtip, lower the nose slightly to lower the airplane to the correct pivotal altitude, bringing the pylon back to the wingtip. As the airplane completes the circle and turns toward a downwind heading, roll out on a heading with crab into the wind so the airplane will arrive at a point downwind of the second pylon. Upon reaching the point where the lateral axis is near the pylon, start the turn, keeping the relationship between the wingtip and the pylon in the same manner as in the first turn. Use a rudder only to keep the turns coordinated and not to keep the pylon on the wingtip. Next we'll cover the chandelle. The chandelle is a maximum performance climbing turn beginning near maneuvering speed and ending at minimum controllable airspeed, heading in the opposite direction. First, clear the area and start at least 1,500 feet AGL since there's a possibility you might stall. Begin heading crosswind and make the turn into the wind so you won't be blown out of the area. During the first half of the turn, bank angle is constant while pitch increases. During the second half, pitch remains constant while bank angle decreases. Pick out a ground reference point at 90 degrees and 180 degrees of turn. Start at any speed no greater than the maximum entry speed recommended by the manufacturer or maneuvering speed if none is recommended. Power should be set to cruise. Roll into a coordinated turn with a bank angle no greater than approximately 30 degrees. Maintaining this bank angle, smoothly increase pitch so that after 90 degrees of turn, pitch is at a maximum. Maintaining this pitch, smoothly decrease the bank angle so that after 180 degrees, wings are level and a nose high attitude at minimum controllable airspeed. This attitude should be held momentarily while at MCA, then gently reduced to return to straight and level flight. The turn will be kept coordinated by changing rudder pressure while the airspeed, pitch, and bank change. Practice chandelles both to the left and the right to discover the different forces necessary during the two turns.
I've noticed that the control forces are different depending which way I'm turning.
That's correct, and it's a good idea to practice in both directions so that you can determine the forces necessary to maintain the turn coordinated in a chandelle to the right or a chandelle to the left, which really leads us to the last flight maneuver that we'll be discussing, lazy eights. The lazy eight consists of two 180-degree turns in opposite directions while making a climb and descent in a symmetrical pattern during each of the turns. At no time during the maneuver is the airplane flown straight and level. Clear the area of other traffic. Start crosswind, turning into the wind as you did in the chandelle. Pick ground reference points at 45, 90, and 135 degrees of turn. At the entry, the airplane is in straight and level flight at normal cruise power and at the airspeed recommended by the manufacturer, or VA. The correct power setting during a maneuver is that which will maintain the altitude for the maximum and minimum airspeeds used during the 8. Start a gradual climbing turn in the direction of the 45-degree reference point. After 45 degrees of turn, the pitch angle is at a maximum and the bank angle should be continuing to increase. The nose should then start coming down toward the horizon. At 90 degrees, the nose should be passing through the horizon, bank should be at the maximum angle of approximately 30 degrees, and airspeed should be 5 to 10 knots above stall. When at 135 degrees, pitch should be at its lowest angle and bank should be slowly decreasing. At the 180-degree point, the airplane should be at the same altitude and airspeed as at entry and moving through level flight into a climbing turn in the opposite direction. Coordination is a large part of this maneuver, with rudder pressure varying as airspeed, bank angle, and pitch change. Because of torque, more right rudder pressure will be required in climbing turns to the right than to the left. And remember, this is a lazy 8, indicating that the speed that we conduct this maneuver is slow and controlled, or lazy. That's about all I've got to cover. Do you have any questions?
No, I think we've covered everything.
Okay, well, why don't we go ahead and put all this theory into practice by going out and fly.
Great.
It never hurts to review, especially if you're uncertain about proper procedures. Sometimes a review like this makes a world of difference in mastering these skills. Let's see how Barbara does after her review. This is also an opportunity for you to test your knowledge on these flying maneuvers.
Okay, Barb, let's do steep turns, but before we start the maneuver, I'd like you to go over, in your own mind, the steps of the maneuver before you do it.
Let's see, I need to do my clearing turn first, and then maintain maneuvering speed or less, roll into a bank 50 to 60 degrees, and adjust my power as I roll in and roll out, and maintain altitude. So I'll go ahead and do my clearing turn to the left first.
Let's review those steps for steep turns one more time. Clear the area. Enter at maneuvering speed or below. Maintain a bank angle of 50 to 60 degrees. Add power as necessary to maintain airspeed. Maintain a constant altitude.
Okay, that was good. Now, let's do the rectangular pattern. And again, I want the steps first before you actually start the maneuver.
I need to clear the area, use an altitude that's between 600 and 1,000 feet above the ground, keep my airspeed constant. When I fly the rectangular course, I need to stay the same distance away from the field and vary my bank depending on the ground speed. Okay, I'm going to roll into a clearing turn to the left.
Once again, those steps for rectangular pattern are: clear the area, maintain a constant altitude of 600 to 1,000 feet above ground level, keep the airspeed constant, make a rectangular track equidistant from the field by varying bank and crab angle. Angle of bank depends upon ground speed.
Okay, real good. Now let's do S turns.
Okay, I need to clear the area and use an altitude that's at least 500 feet above the ground. Enter downwind and vary my bank according to where the wind's coming from, and stay the same distance from the road in each loop. Okay, I'm going to go ahead and do a clearing turn now.
And again, the steps for S turns are: clear the area, maintain a constant altitude of at least 500 feet, enter downwind, the bank depends upon the ground speed, maintain equal half circles on each side of the road by varying bank and crab angle.
Okay, good. Now we'll do turns about a point.
Okay, I need to clear the area, use an altitude that's at least 500 feet above the ground, enter on a downwind heading, and maintain a constant radius around the point, and then vary the bank according to the wind.
Again, the steps for turns about a point are: clear the area, maintain an altitude of at least 500 feet, enter downwind at a maximum bank angle of no more than 45 degrees, maintain a constant radius circle by varying the bank angle and crab angle. The angle of bank depends upon ground speed.
Okay, good. Now we'll do 8s around pylons.
Okay, this is kind of like the turns around a point. I need to clear the area first, use an altitude that's at least 500 feet above the ground, enter downwind, maintain constant radius around the point, and then vary my bank with the wind so that I can maintain that constant radius. All right, let's do the clearing turn.
Once again, the steps for 8s around pylons are: clear the area, maintain an altitude of at least 500 feet, enter downwind, maintain a constant radius circle by varying the bank and crab angle. The angle of bank depends upon ground speed.
Okay, good. Now we'll do 8s on pylons.
I need to clear the area, enter downwind, and then keep the point centered by varying the altitude or use the pivotal altitude, and then crab during the straight flight in between the points. So clear over to the right here.
Again, the steps for 8s on pylons are: clear the area, enter downwind, keep the pylon centered on the wingtip by varying the altitude. Remember to crab during straight flight between the turns.
Good. Now, steep spirals.
Okay, again I need to clear the area, bring the carb heat on, the power back, establish my glide speed, maintain a constant radius around the point, vary my bank according to the ground speed, clear the engine on each turn, and then roll out at least 500 feet above the ground. Clearing turn to the right.
To review the steps for steep spirals: clear the area, carburetor heat on, close the throttle, establish glide speed, keep a constant radius around the point by varying the bank angle. The bank depends upon the ground speed, and the steepest bank angle should be 50 to 55 degrees. Clear the engine during each turn, preferably while heading upwind, and complete the maneuver above 500 feet.
Good job. Now do a chandelle.
Okay, I need to clear the area and start at 1,500 feet above the ground at least. Make my turn into the wind, enter at maneuvering speed or below. In my first 90 degrees of turn, I'll have a constant bank and I'll be changing the pitch. And then the second 90 degrees, I'll be changing the bank but maintain a constant pitch. And then I'll wind up 180 degrees away from where I started at minimum controllable airspeed. So we'll go ahead and start with the clearing turn to the left.
The steps for the chandelle, once again, are: clear the area, start the maneuver at least 1,500 feet above ground level, turn into the wind to stay in the practice area, enter at maneuvering speed or below. During the first 90 degrees of the maneuver, maintain a constant bank while changing pitch. During the second 90 degrees of the maneuver, change the bank while maintaining constant pitch. End the maneuver at 180 degrees of turn and minimum controllable airspeed.
Okay, good. Now we'll do a lazy 8.
Okay, clear the area. And then my first turn is into the wind. I need to enter the maneuver at maneuvering speed. At the 45-degree reference point, I'll have the maximum pitch and be increasing my bank. At the 90-degree reference, I'll have 0 degrees of pitch and 30 degrees of bank. And then at the 135-degree reference, I'll have the minimum pitch and decreasing bank until I get back to 180 degrees and I wind up at the same altitude and the same airspeed. And I have to remember to do this really lazy. Okay, we'll start with our clearing turn to the right.
And again, the steps for lazy 8 are clear the area, turn into the wind to stay in the practice area, enter at maneuvering speed. At the 45-degree point, you should be at maximum pitch and increasing your bank angle. At the 90-degree point, you should be at 0 degrees of pitch and 30 degrees of bank. At the 135-degree point, you should be at minimum pitch with decreasing bank. At the 180-degree point, you should be at the same altitude and the same airspeed as at entry. Remember, lazy.
Nice job, Barb.
Thank you.
Flight maneuvers can be difficult, whether you're just learning or have many hours in the air. These maneuvers require more than just understanding. They require the right coordination. But I'm sure that with this review and lots of practice, you'll master them all.
Well, the investigation revealed that the pilot was a private pilot with 160 hours. He'd got his fuel selector positioned between tanks, so it was a case of fuel starvation. I'd say most probably he just panicked, pulled up right into a stall.
This pilot had 500 hours and some 400 in type. According to the surviving passenger, the pilot became distracted while cranking the gear down. Didn't pay attention to flying. He simply stalled.
This man had a commercial ticket and a couple of thousand hours. He was inspecting a power line. A witness said the aircraft rolled into a steep turn to double back in its course. Too steep, I guess. He just plain stalled.
A student pilot takes off for an hour of solo air work. He'll spend part of it practicing stalls. You know what a stall is and how to recover from it. You learn just like this student in your first few hours of instruction. All pilots know it, or knew it once. Yet stalling accidents occur on the average more than once a day. They account for about a quarter of the general aviation accidents. Why do pilots who know better get themselves involved in stall accidents? Not just the students and low-time pilots, but the average pilots and even the old hands with 1,000 hours or several thousand. This film will review the information you need to know about stalls and about spins, when they're most apt to occur, how to recognize the onset, and how to recover safely. Let's make clear right from the outset that you can stall at any power setting, at any normal airspeed, and in any attitude. Most pilots think of a stall as something that only happens when you slow down your airspeed, like this. But you can also stall like this. High speed, sudden control movement, and stall. A little review of theory will explain the factors involved. Consider this airfoil as the aircraft goes into a glide. The flight path is like this, and the relative wind affecting the wing is like this. The angle between the chord line of the airfoil and the relative wind is the angle of attack. Within limits, if you coordinate changes of attitude with changes in power setting, the angle of attack remains the same, providing the speed remains constant. But any time you change power while holding the attitude constant, the angle of attack changes. And any time you change attitude while maintaining the power setting, the angle of attack changes. Ordinarily, there's no need to think about angle of attack when you fly. You get on perfectly well without drawing diagrams in your head. It's only when the angle of attack becomes quite large that it gets to be a problem. The smoke tunnel lets you see what happens. First, from level flight, we pull up the nose. The angle of attack increases until finally the air can no longer flow smoothly over the wing. This is the critical angle of attack, and the result is reduction in lift, and the aircraft stalls. Now watch. The same thing can happen when you're in a climb. It can happen when you're in a glide. And it can even happen when you're in a dive. For a particular airfoil section, the critical angle of attack is always the same. No matter what the attitude, power, and airspeed, the airfoil will always stall if it reaches the critical angle of attack. The important point is this. It's wrong to think of a stall as something that happens at a particular airspeed. The speed at which a stall occurs depends on a number of things. For example, remember that stall speed increases with G loading. In this aircraft, flaps up, the stall speed in level flight is 72 miles per hour. The G loading of a 20-degree bank increases the stall speed slightly. At a 40-degree bank, the stall speed jumps appreciably. Here's a bank of 60 degrees. Look at the stall speed. Another factor that has a bearing on stall speed is weight. This aircraft, with fuel tanks half full and one person on board, has a stall speed of 65 miles per hour. But at max gross weight, the stall speed goes up to 70 miles per hour. Also, stall speed may be lowered on most aircraft by extending the flaps. Curiously enough, power setting also affects stall speed. The reason is that prop thrust induces additional air velocity over part of the wing, giving a little extra lift. Cut the power, and that extra lift disappears, thus increasing the stall speed. Here's where it can make a difference. You've let the airspeed get somewhat low, and suddenly you realize you're a good bit too high. So you chop the power. Wave off and go around. The moral is, don't chop power when you're too slow because power affects stall speed. Enough of the theory, let's get on to the flying. First topic, how do you know when you're approaching a stall? One way is from the stall warning device in the aircraft. Another method is the stall warning light. But you don't always have to rely on mechanical systems. The aircraft itself may tell you when it's approaching or entering a stall, and you should learn to recognize the signs characteristic of aircraft you fly. The controls become mushy as you near a stall. Because of the reduced airflow, control effectiveness is reduced, and it takes an extra amount of displacement to produce a given response. In some situations, you may also be able to hear the approaching stall. As the airspeed decreases, the engine sound changes and the wind sound decreases. Listen. A heads-up pilot learns to use sound cues in a lot of ways. Some aircraft give another kind of indication of an approaching stall. They begin to buff it. As for what happens when the aircraft enters a stall, you don't have to be told about that. You already know that normally, in most aircraft, the nose pitches down and one wing may drop. These actions are usually more pronounced when you stall with power on. However, it doesn't always happen like that. Some aircraft can stall without a clean brake. Picture this situation. You're on downwind behind a slower aircraft, and you've reduced power to keep from running him down. You realize you're losing altitude. So you add a little power and come back on the elevator. No effect. This time you pour it on and haul way back. Still going down. But look at your airspeed. You're in a stall. In this situation, the aircraft just mushes down. Power and back pressure won't help. You'll keep going down until you take definite recovery action. Which brings us to the next point, how to recover from a stall. The exact technique varies somewhat from one aircraft to another, but the general principles are the same. First, reduce back pressure. Second, add full power. Third, level the wings with coordinated use of controls. Here's the way it goes. You enter a stall. Applying forward pressure decreases the angle of attack. Remember, if you add power while holding back pressure, the nose will tend to rise, aggravating the stalled condition. Use full power. Don't overboost a supercharged engine, of course, but unless planned otherwise for training purposes, use full power. Then level the wings with coordinated use of aileron and rudder, and recover to the desired flight attitude. The procedure is essentially the same for any type of stall. Here's an approach stall, flaps down, power off, gliding in a turn. Wheel forward, full power, level the wings. The departure stall in a climbing turn. You can expect a more pronounced tendency to roll in a power-on stall. The accelerated stall is a special case, since it can happen at any normal airspeed. It most often occurs when the pilot tries to tighten the turn or correct the altitude with back pressure and pulls back too rapidly. It's the increased G-loading that leads to trouble. Recover from the stall first, then level the wings. Excessive or early up-elevator use during stall recovery can cause a secondary stall. Spins continue to be a factor in accidents. Therefore, you should know what a spin is, how it occurs, and how to recover. The most important thing to know is a spin is an aggravated stall. Aggravated means you're continuing to apply the control pressure which caused the stall, usually back pressure, and possibly rudder. If you enter a spin, there may be a recommended recovery technique for your aircraft, but if it's unknown or not given, the following steps should be taken. Power usually aggravates a stall, so close the throttle. Remember, it's easy to become disoriented in this case. The aircraft is spinning to the left, which makes it appear as if the Earth is spinning to the right. So the second step, use full opposite rudder, right rudder in this case. Notice the attitude. The nose is way down, but well short of vertical. Yet from the cockpit, you may get the feeling of heading straight for the ground. It's important to realize this is just an illusion. Because the third recovery step is reduce back pressure with enough brisk forward elevator to ensure recovery. As the rotation stops, release rudder pressure and smoothly apply elevator to raise the nose. The airspeed increases rapidly during recovery. Avoid excessive G-loads, but keep the nose rising steadily to the desired flight attitude. Don't yank. That could overstress the aircraft or cause a secondary stall. Remember that the specific details of spin recovery varies with the type of aircraft. Learn the correct procedures for the aircraft you fly. Earlier, we posed the question, why do experienced pilots become the victims of stall accidents? Let's answer that now by looking at some of the common situations that account for the once-everyday accident rate. The most common underlying reason is distraction. The pilot's attention is diverted because he's searching the ground, or studying a chart, or checking on some malfunction, and he forgets that his #1 task is to fly the airplane. That's particularly a problem when you're flying close to the ground for search and rescue, cattle counting or roundup and the like. If you must fly at very low altitude, keep ahead of your airplane and avoid extreme maneuvers and sudden control movements. Here's a situation that's gotten many pilots into trouble, taking off from a short field, with trees or power lines at the far end. Even when he can clear the obstacle, there's a strong urge to haul the airplane off the ground before it's got flying speed or to try climbing or banking too steeply. Another common cause of stalling is retracting the flaps too quickly before airspeed is above the flaps up stall speed. No time of flight offers more hazards for a stall accident than the approach for landing, because you've got so many things to think about at once. Here's a pair of situations that too often head to inadvertent stalls. First, the trim tab stall. The pilot has his aircraft trimmed just right for the approach. Then, realizing he's too high, or the runway isn't clear, he decides to go around. He pours the coal to it, forgetting his trim. Forgetting he'll need to hold forward pressure to maintain pitch attitude. The nose pops up, stall. Finally, the cross-control stall. The pilot begins a turn onto final and discovers he's overshooting. Now, he's always heard you shouldn't make a steep turn at low altitude, so he decides he'll just skid back to course with rudder. This tends to make a wing drop. He corrects with a little opposite aileron. Then he finds the nose going down, so he applies a little back pressure. As he continues to hold rudder, he finds he gradually needs more and more opposite aileron and back pressure. This is a setup for disaster. One last point, probably the most important point of all, yet the books never tell you. Imagine yourself there in the pilot's seat. You always practice stalls at altitude, but the unintentional stalls often happen near the ground. And here you may forget all the good practice. Technique says forward on the wheel, but your instinct says get away from the ground, pull up. Many pilots have become statistics because they listen to instinct in a moment of crisis. Panic is your worst enemy. So what's the answer? Practice. Practice flight at minimum controllable airspeed. An excellent way to keep proficient at recognizing the mushy feel of the controls that may warn of an approaching stall. And practice your stalls. Knowing their causes will help you avoid the inadvertent stall. Practice often. Make it a habit to go out and work on stalling for safety.